Welcome everybody to Optimization in Oslo. We're very happy to have Peng Chen from Georgia Tech, who's speaking to us remotely today. He's going to talk about Mr. DINO or MR-DINO, derivative informed neural operators for PDE optimization under uncertainty. We're very happy to have him. So Peng, the floor is yours.
Thank you very much, Thomas, for the invitation. I'm very glad to share this recent work with you. So this is essentially we're building some sort of like a surrogate models to solve this PDE-constrained optimization and under high-dimensional uncertainty. So this work is joined with DC Law, a PhD student at UT Austin that I'm co-advising, and Thomas Oliver Rosberry, and also Professor Omar Gattas. So let me start with a few application problems that we worked on. So the first is on the left, you can see this is sort of like the turbulence flow. In fact, this is an application of turbulence and combustion. So we have like the fuel and oxygen coming in, and we want to fully mix this different like components, and then so there is a velocity profile control here. So this is an optimal control problem and subject to, like this is a PDE set of like a PDE problems for their turbulence combustion. And then there is uncertainty, which is the turbulence viscosity. It's a model the turbulence viscosity as an uncertain random field. And the second example is about their management for water extraction. And so you can see there is a well here. We can scan sort of like a monitor essentially this change, the height change of this area. So there are some water in it we can extract for, let's say, like agriculture use or some other use. And while we want to extract as much as possible the water, but we want to avoid the collapse of the aquifer. So this is essentially optimal management for water extraction. And we have a lot of uncertainty here, in particular the uncertain storage field and also the permeability field. There is a certain constraint. For instance, there is a chance constraint or probability constraint that the aquifer should not be collapsed. Let's say if there is a certain drop of the pressure, and we don't want the pressure to exceed a certain value, a threshold value in probability. And then the third example is about a flow rate control. So I have an injection well and extraction well, and I want to control the flow rate of their oil production. And this can be described by a simple model like a dusty flow, and it's subject to uncertain permeability field. So the third example is you see here is a submarine, and we want to design some sort of like a material, let's say a metamaterial, an acoustic or electromagnetic metamaterials the surrounding object, and I want to cloak the object. Essentially, I want to hide the object from detection. Let's say if you send some waves, and you want to like essentially eliminate all this scattered wave. How do you design this material around this object? And there is a manufacturing error and uncertainty of the material and topology uncertainty. So how do you design this material subject to this different kinds of uncertainty? And also, the PD model could be the acoustic model, the electromagnetic model. All right, so these are some of the applications I've been working on. In particular, I'd like to mention one of the applications that I've been recently working on. It's a nanomaterial. It's a so-called directed self-assembly material. Well, let me see if I can remove this stuff somewhere else. Yeah, okay. So essentially, we have the die block polymer. There are two segments, A and B, in very small scale. And that tends to have a certain repulsion or attraction force. So if we place the material at the same place, and they will sort of like a self-assembly into different morphology, different pattern. For instance, here, if we just place a lot of the material at the beginning, like mix them completely, then after a certain time, it will have a certain phase separation. And So there is no direction, or there is no like control for this material self-assembly process. But however, we can use this kind of a self-processing, self-assembly to manufacture some materials they want, in particular some targeted morphology. Let's say in semiconductor, in this sector, we want to manufacture some directed, morphology, targeted morphology like this. It's parallel pattern. So how do you do that, right? We can place some chemical substrate like here. We can place this substrate, and this substrate, they have a certain attraction for one part of the material, let's say. And depending on how do you place this chemical substrate here, that will form into different morphology. And this is the ideal one that we want to place. This is a so-called directed phase separation. We have the target morphology. And the reason to have this chemical substrate, you have a wider distance compared to this morphology that, for instance, if you want to manufacture some, let's say 1 nanometer material, and we can place maybe 5 nanometer material here. So this can be doable, but this 1 nanometer may not be done directly. So we might have some other targeted morphology. For instance, this is a bit more interesting morphology. So we can place some directed, let's say, guided post, and these are the guided posts we can place at certain different locations. So if you place a guided post at the beginning, the material are completely mixed, and if you place this guided post after a while, there will self-assembly into certain different morphology. For instance, this is one of their equilibrium morphology, and it is quite similar to this one. But however, since the material starting at the beginning, they're completely mixed. It's sort of like a random field, a Gaussian random field. You can think of it like it's Gaussian white noise because the material is a very small scale. And then after the self-assembling process, they might form into different morphology, right? Like a different phase separation. So we don't want this kind of separation, and this is what we call the defect. It's quite different from this target morphology. So this kind of defect can be caused by different uncertainties in the process, like the initial condition. So essentially, how to mix the material together. We don't really have a good control of the mixture at the beginning, in fact. And there's also some manufacturing precision, like the environment temperature or some other environment variables. And also it depends on the material property, the purity of the material property, for instance. So subject to all this different uncertainty, how do we design this guided post in order to achieve this target morphology, right? This is the problem that can formulate it as a PDE-constrained optimization under uncertainty. So here, a bit more mathematically, we have a state variable u in a separable binary space. U here, calligraphic u, and we have a parameter, uncertain parameter or random parameter. And this parameter, as we've shown in the different application, they're random fields or some other case like a stochastic process, they're infinite dimensional. And after discretization, it could be very high dimensional. And we have an optimization variable z. Z is in some admissible set, which is in some control or design space, z here. A consume is also let's say some like a Hilbert space for it could be finite dimensional, could be parametric, and we can allow different forms of this optimization variable. Like for instance, the OiO for the OiO production, this z is time dependent, and h at several different space location. But for the metamaterial design, this z would be the the topology of the material that we want to design in the field. So we assume here this is our PD model. We write it as a residual form. So we have the state variable, the parameter, and the control variable or design variable. And then typically assume this operator, like a solution operator, is differentiable with respect to both the parameter m and also with respect to the optimization variable, where we can use some derivative-based method. or we can assume, for instance, it's a sub-differentiable. We can at least detect the derivatives. Because their optimization variable could be quite high dimensional, and then this optimization method based on gradient based, like either the first order, second order, especially a second order method, it could be very relevant here because it's accelerated their optimization quite significantly. Okay, now we assume we have a optimization objective of Q, and a Q is mapped from their solution function space to some let's say real variable, and so we have a parameter that is uncertain, follow certain different probability distribution, nu m. It could be high dimensional after discretization, or if infinite dimensional in the continuous field, like a Gaussian running field, for instance. And then this Q now depends on M and Z through this solution U here. So it is a random variable for any fixed optimization variable Z, because it depends on M. So to quantify the cost function or objective function we want to minimize, we define some risk measure, like a rho of a Q. For instance, it could be expectation, could be a variance or standard deviation, or some other statistical quantity. And here's a problem we want to solve: the minimization of this cost functional respect to this optimization variable Z. And there are two components, two parts. The first part is a statistical measure of this objective function Q, and another is the penalty term or regularization term. And we have this PDE-Constrained here. Okay, so one particular type of a risk measure, this so-called conditional value at risk for different probability level beta from 0 to 1 is given as follows. First, you have the value at risk. And for instance, here you have this Q takes value from 0 to maybe 70 or even more. And here's a density for this Q, as a density function for this Q. And it can define a value at risk here for a certain probability level. Here you see we have the probability of 1 minus beta. So the area of this part would be beta. The area of this tau would be 1 minus beta. So we can define a value at risk as a quantile, a certain quantile, like a beta quantile here is given as this one. And then we can define a conditional value at risk as a expectation of this objective function for this objective function to be larger than this quantile. And we can average it over, we can divide it by, rescaled by this probability here. This is a conditional value at risk. Depending on, different beta value. For instance, if you take beta as 0, then that essentially means, it takes the leftmost point. And if you take the average, then that is essentially the mean, right? There's a risk neutral statistical measure. And if you take beta equals to 1 here, and it is the maximum, so essentially this will be the worst case scenario you're solving the robust optimization problem. For a general beta here, we can reformulate this conditional value at risk as this formula. It becomes a minimization problem with a certain variable t, and here is a max of x and 0, and it is a non-differentiable at a certain point, right? You can allow the sub-differentiation, and so here we can apply, for instance, some smooth approximation at this point, as done in this paper by Jucuri and Thomas. So for this measure, for instance, we have this problem to solve. A very straightforward approximation here would be, we can apply sample best average approximation, right? Sample average approximation. We can draw a lot of samples, MI, from the probability distribution, and then we can compute this sample average approximation of this expectation here. And then we would have a lot of constraint, like the PDE-Constrained at each of the sample. So there are many PDE-Constrained, and you can solve this optimization problem using this sample average approximation. But clearly you can see the computational cost could be quite large because you might need a lot of samples here. And typically the challenge would be the expectation or the estimation of the risk measure require many samples if you use a sample average approximation, because typically the Monte Carlo type of a sampling error decays in statistics or in arbitrary norm in probability space as n to the power minus 1/2, and it's pretty slow, so you need a lot of samples. And secondly, each sample require a PD solve, also plus some adjoining PD solve to compute the gradient, right? So total number of PD solve is proportional to the number of optimization iteration times the number of samples. Of course, you can accelerate it by some adaptive sampling strategy, and but when the PD solve is like quite expensive, for instance, then this becomes definitely quite a challenge to solve. In particular, for instance, you have some larger scale PD multiphysics and multi-scale problems. And there are some other additional challenges. For instance, if you have some constraint on their optimization variable, or constraint on their state variable, or some probability constraint on both state and optimization variables, that's an additional challenge. So over the years, many different kinds of methods been developed to address these challenges. For instance, we have this Monte Carlo and also multi-level Monte Carlo, and also some quasi-Monte Carlo method. And there are also some stochastic collocation, generalized polynomial choice method developed in the early years, about a decade ago, and also some model reduction techniques and low-rank approximation, and also some recent work on Taylor approximation and also neural network approximations. There's a long list of references, but it's still like a partial of what's being done in the community. So there are some early works and about this different methods. In particular, we also contributed to this kind of problems over the years. So for instance, at the beginning, we considered about this optimal control problem for advention-dominated elliptic problem. And there we used a sparse grid, essentially stochastic collocation. And later on, we developed some weighted reduced basis method, essentially probability, for instance, for the uncertain variable, how to properly design your reduced basis method with certain weight and to be more efficient. And we applied this weighted reduced basis method for optimal control problems, and also extended to multi-level and weighted reduced basis method. Essentially, it's a class of a model order reduction. And then we developed this Taylor approximation, and on top of a Taylor approximation, which is a surrogate model, we developed this variance reduction for this kind of problems. And then we applied and also further extended this Taylor approximation for some chance-constrained optimization problem. If you have some probability constraint or chance constraint on your, let's say, state variable or some other related quantity of interest. And then we have some interesting applications like, as I mentioned before, but in particular, this one, optimal design acoustic metamaterials on uncertainty, essentially topology optimization problem. And more recently, we also have some analysis on, like here to solve this kind of problems, a lot of approximation. For instance, you have the sample average approximation, you have the PDE discretization, and you also have the stochastic optimization problem. You have let's say the smooth approximation if you have like a non-smooth problem, right? And also, for instance, for like a chance constraint optimization problem, or some other moment constraint optimization problem, you might need some, let's say, relaxation or penalty. So there's a lot of different kinds of approximations, right? And we considered about 5 different, put them together in a consistent way in a framework, and we analyzed the performance bound for PDE-constrained optimization under all these different kinds of uncertainties. So essentially, the conclusion is under suitable assumption for the approximations, we can actually achieve, essentially for the objective function J here, it would be as close as possible to their, let's say, without any approximation up to a certain tolerance, the tolerance for the approximation and the tolerance for the optimization stopping criteria. So in the last work, we developed this derivative informed neural operator, which is the topic we're going to talk about this today. So let's take a closer look. So essentially, it is a surrogate type of approximation. We can replace high fidelity solution or evaluation of the PDE problem by low fidelity surrogate. And so there's some challenges for constructing the surrogate for OiO problem. The first is we wanted the accuracy over the joint space of a high dimensional input and also output. So that for the input, we would have the input in both the parameter, uncertain parameter, and also the optimization variable, right? And also for the output, we have the solution manifold. Formally, they're infinite dimensional with discretization is high dimensional. We denoted the dimension of dm and du, and also it's finite but moderate dimension for the optimization variables. Here we assume dz could be much smaller than this very high dimensional discretization, like millions of them. And so we want to compute the gradient that's reliable with respect to their optimization variable. Typically, surrogate model may not be giving you the reliable gradient, especially if you train a neural network. And then what if you have like a limited training data? For instance, if you solve the PDE problem, which is already expensive, you cannot afford to solve many of them, right? And we can only have a limited number of training data. All right, so this is a general solution operator. We replace our PDE solution operator, which depends on M and Z, and we replace it by a neural network. The input of the neural network would be M and Z now. So once we construct this neural network, we can quickly, evaluate this solution, and also can draw samples from M, can evaluate this neural network, becomes very fast. So and also becomes reusable for different objective function, right? Like if you consider about different risk measures or penalty terms or different objective functions, this solution operator can be repeatedly used. So over the years, of different kinds of solution operator or neural operator developed, like their Fourier neural operator, DeepNet, and also their reduced basis based neural operator, like the learning ROM or POD deep learning ROM, and some PCA net developed pretty early on. And also we developed this derivative informed projected net, and also the DINO derivative informed neural operator. But the question is, can the neural operator be used for the OiO problem, optimization on uncertainty, in a cost-effective manner? By cost-effective manner, we mean it takes PDE solutions to construct this neural operator, right? If it takes more PDE solutions, more PDE samples to construct the neural operator, and then you would use in the OiO problem, then definitely it's not effective, right? It's not efficient. So essentially, we want to reduce the total number of PDE solved by using this surrogate model, including the training for the surrogate model. All right, so here's a basic architecture of our Mr. DINO, the so-called multi-input. We have both the parameter input and also optimization input, and reduced basis. So we projected the high dimensional parameter into low dimensions, and the derivative informed. And so we want to take the derivative of the neural operator with respect to the optimization variable into account for the construction of the neural operator. So essentially, so here you can see in this general framework, we have the high dimensional parameter with discretizations M, and we can project it down into some low dimensions by PCA or Kahunian law of expansion, let's say from millions to a few tens or hundreds, and then the neural network becomes much smaller scale, right? So optimization variable as additional input here. For the output solution, we also do their dimension reduction, like say by POD or some other dimension, nonlinear dimension reduction techniques, like some other decoder. So then we would only need to construct a neural network in the reduced dimension. And instead of like from millions to millions, you only need to like construct a neural network, perhaps from a few tens to a few tens or hundreds. And then here's their architecture for the neural network. You have the projection input, projection output, and then you construct the neural network. Here we use ResNet and adaptive construction of the ResNet. And then we put them in their, loss function for the training of the neural network. The first term is a mismatch between their neural network and our solution. And the second is the mismatch between our derivative or the Jacobian of the neural operator with respect to the optimization variable and the true, Jacobian. But of course, this is a second order operator, and we measured in their Hilbert-Smith norm here. And in discrete space corresponding to the Fourier forbiddance norm. All right, so here we have some scalable data generation training because we have this reduced space. So we reduce the dimension from this high dimension to the low dimensions for the input and output. And in fact, we can, formulate this loss function in the reduced space. Now here you have the projection here, and you have the neural network, which is in the reduced space, right? And also now you can compute this derivative also in the reduced space. And now you only need to take the derivative of the neural network with respect to z. And z is typically moderate dimension. So we're okay with it. We do not do further dimension reduction for it. But if z is also coming from, let's say, high dimensional discretization, we can also do the dimension reduction there too. And then we can generate the data by sampling from the adjoining parameter space and also optimization space. So for the Jacobian data in particular, for the PDE solution, we can just solve the PDE, right? For the Jacobian here, we need to compute this term. And imagine this z could be like 100 dimensions. Still, you need to solve, let's say, a lot of, well, this Jacobian is essentially, you have to solve many PDEs, right? But fortunately, those are linear PDEs you need to solve. And in particular, we only need to solve in the reduced dimension, this many PDEs, like the minimum of RU. RU is a reduced dimension for the output, and also DZ. DZ is the input of the optimization variable, because we can use a Jacobian action. That's like a Jacobian acting on, let's say, the reduced space basis. So this Jacobian is computed by solving the linear problem. We have a, this linear operator or linearized operator, which is a derivative of the original PDE operator with respect to their U here, evaluated a given point, given samples. Okay, so now since all this differential operator for each of the MI and given U as a linearized operator is the same, right? Or you can solve it for a joining problem, depending on the dimension of this RU and DZ. And in fact, we can factorize this linear operator and use it again and again, right? Or we can reuse it as a preconditioner in order to achieve additional computational saving here. And some additional cost after the computing. So essentially, as long as we solve this PDE problem, the additional cost to compute the Jacobian is not that much. We're going to show some numbers a bit later on. So here's one example. You have they're essentially the diffusion problem and reaction problem have a nonlinearity in the reaction. And so we have a control in here, source control, and we assume homogeneous Dirichlet boundary condition. We have a random parameter following Gauss random field. I have the mean and also a Martin covariance operator given here. It is a inverse of the bi-Laplacian with additional term here. We have a parameter gamma and delta. These parameters, they're actually controlling their variance and also the correlation of the random field. And we assume our control variable, we have a 49 control variable. Control variable are bounded from -4 to 4. And then we have two targeted functions. The first is a tracking type of objective function. This is we have a target. I want to match this target. There's additional one I'm going to show later on. So minimize this C var over admissible set. Essentially, this is our admissible set subject to the PDE constraint, right? So we can optimize this problem by using BFGS with a box constraint for the optimization problem and with a certain smooth approximation of a C var criteria. So here's some of the specific numbers. If we solve it by find element in a mesh of 64 by 64, and the state variable would be 4,000 dimensional, and parameters are also 4,000 dimensional. Control variable is 49. So can reduce the dimension by the PCA or POD So into about 100 and 300 for their parameter and for their state variable. So we have two different dimension reduction. One is a smaller dimension reduction, it's 100 with 150 parameter, and another a larger, essentially a large number of bases with 300 and 100 bases. So we can construct a small neural network and also a large neural network. Well, relatively speaking, a larger neural network. And we use a soft plus activation ADAM optimizer with adaptive learning rate to solve this problem. And the neural network itself is a ResNet. So here are some results. We have the comparison here of the different large and small neural network, and we use the multi-input neural operator and also derivative informed neural operator. As you can see here, this is the mean relative L2 error for the solution operator, and also here's a mean relative error for the Jacobian. So on the left, you can see for the neural network with the derivative informed, you can you can improve the accuracy for the approximation of the solutions of U, right? So also on the right, you can see it improves the Jacobian or the derivative accuracy. With the increasing number of training samples, you can have a higher accuracy, and but it's not that much improvement compared to, let's say, if you use and do not use a Jacobian. And another point is, with a relatively small neural network here, like here. So with the small neural network, if you increase the number of training data, then the accuracy is sort of like a stagnated here, get stagnated, right? If you use a larger neural network, then you can have additional improvement for the accuracy. And yeah, so all right, so this is a there are target state variable. This is our prediction by neural operator, and this is of the PDE solution. So after you optimize the problem, you solve the optimal control. So if you solve the PDE-based optimal control, but just solving the PDEs with one element, this is the target, and this is if you solve by using a surrogate. And we have the random parameter here as random field, and these are the optimal control variables. Let's take a look at their computational cost here. So for the PDE solves, let's say, how many PDE do we need to solve, right? So in the PDE-based solution approach, like in the offline stage, you don't have to solve any PDE. Just in the online, you have to solve many PDEs by the sample average approximation at each iteration. And for the neural operator, you just need to generate the data offline and train the surrogate. And in the online, there is no PDE solve anymore. And for the accuracy of the bias and variance comparison, so there is no bias with the PDE solve if you assume there is no discretization error, or if you take this, a PDE discretization as a high fidelity approximation, and you don't consider it as bias. And there is a variance because you use a sample average approximation. So there is a sample approximation error, right? This is it could be relatively large because you cannot afford to use many PDEs. And then in the neural operator case, there is approximation error. But for the variance in the sample average approximation, you can draw many samples, right? You can nail down the sample average approximation. Essentially, the variance here is small. So you see, we can measure the cost by a number of state PDE solves, and we solve the problem with the reference ground truth solution with a sample size. We use a significant number, a larger number of sample size for the PDE-based approach. So we take this as the ground truth reference solution. And then we can compare the CVAR at the optimal controls. Once we arrive at the optimal controls, we can compare just the CVAR, the relative accuracy of the CVAR, like the CVAR evaluated at this one, and also the CVAR evaluated at the reference. And we evaluated the relative error. And this evaluation takes about 8,000 samples. It's large enough here. So now here you can see we have 3 different approaches. One approach is completely PDE-based solution. So with increasing number of sample average approximation samples in each of the iteration, right? So total number of stated PDE to solve also increase. And here is the optimal cost in terms of the relative error for their CVAR. Well, actually, so this is optimal cost. This is CVAR itself, and this is a reference value, the dashed line. So we have two other approaches. One is we use a Jacobian, essentially the Mr. DINO with a derivative training. Another is without a derivative training. So this is this number is 512 up to 4,000. These are corresponding to the number of training samples. And also with increasing number of training samples, there is increasing number of static PDEs we need to solve, right? And you can see here clearly the Mr. DINO beat the other two methods in terms of accuracy and also in terms of number of PDE solves. Like here, if you just use 512 samples to train the neural network, and you would already arrive at the accuracy comparable to the PDE solution here. There is about almost 2 orders magnitude difference between the PDEs you need to solve. And so we have a sinusoidal target here and another quadratic target here. You have a different target functions, and you can see similar performance. And in particular, if you do not use the derivative-based training, right, the neural operator, the planned neural operator you apply here does not perform as well as the PDE approach. Essentially, if you use a lot of PDEs to train this neural operator, and then still you cannot beat the PDE-based approach for the solution of this optimization problem. Like here, even with 16 samples for the PDE approach, you can achieve a high accuracy than their neural operator. Okay, so these are the some of the additional tests for different beta values. Well, let me see. Yeah, so relative optimal. So this is in terms of the relative optimal cost error. Essentially, this is the same as this plotting. The only difference is relative optimal cost error. We measure the error and performance. Essentially, you can see with the Jacobian training and the Mr. DINO, we achieve about a 10 to 100 more sample efficiency compared to the sample average approximation with PD solve. All right, so this is about with different beta value. Previously, we used 0.95. Here is 0.9. It's a similar performance. And the next numerical results is this flow control. So we have a fluid flow. I have a Navier-Stokes equation here, and we have some random inflow like the wind, for instance. This is a bluff body. We want to control on the boundary in order to minimize, let's say here, the drag. If we do not have any control on the boundary, then we have a lot of drag, right? Drag force. And if we control here on the boundary, we can minimize the drag here. So we have a control function on this boundary, which is parametric here. And we assume also the Gauss random field for the input flow field in the x direction. And we also have two different objective functions. The first is this is a symmetric version of their essentially the gradient of this U here, and this is the tracking type. Essentially, we have a target U here. So both of their object function can help to minimize this drag. And we have a penalty term. Essentially, we want to penalize the control we're putting here as a parametric control using B-splines. All right, so here we use Taylor-Hold finite element to solve this problem. The full dimension in the state is 42,000. Reducer dimension is 200. The parameter is 100 on the boundary, right? It's relatively small. And we still perform the reduction in about 100 in 100. And the control is 18 dimensional. And we use similar architecture here with 2 hidden layers of 400 neurons. And here's the result. So essentially, the flow field with no control and optimal control. This is done by the neural surrogate with 256 training samples. And we also have a comparison, cost efficiency comparison. We can see a similar performance. In particular, you see like here, and this one, you really need to use a lot of PDE solves to achieve certain accuracy. But with a relatively small number of PDE training samples, you can already achieve a pretty good accuracy. All right, in particular here, we have a comparison of with Jacobian training or derivative training and without Jacobian training. So on the left, you can see the relative error for the solution operator. Let's say if you use 256 training samples, right? With Jacobian training, the error is about 2%. But if you use 2,000 samples without Jacobian training, you can achieve better accuracy here, right? Because you have more samples to train for the new operator. But however, on the right, you can see this is a relative optimal cost error. Even though the solution operator is not that accurate compared to the without Jacobian training, you can still achieve better accuracy compared to the without Jacobian training here, right? Essentially, the Jacobian training is not only helpful to improve the solution accuracy, but also in particular is helpful to improve the accuracy for their optimization problem. All right, so here's the computational cost comparison. So we have the two problems. One is a semi-linear elliptic, another is 2D Navier-Stokes equation. So for the evaluation by the neural network, one single evaluation takes about this seconds. And if you use the batched version, if we evaluate 2,000 samples at the same time, it's about this 0.1 second. And so you can evaluate the Q and also the gradient of the Q respect to their optimization variable. We properly timed the computational time here. So the conclusion is that compared to the PDE solve, the batched evaluation of the neural network is about 10,000 and 100,000 faster than if you just solve the PDEs using finite element. And here's a computational cost to compute the solution and also it's Jacobian. So one static PDE solve here for the semi-linear elliptic equation is about 1 second, and one LU factorization is about 0.4 second. And then the subsequent LU solve, essentially, we mentioned that we can just factorize this linearized operator once, right? And then you can use it to solve many linear PDEs. So it's negligible. The computational cost is negligible. In particular, for the 2D Navier-Stokes equation, you can see their, the linearized solve is negligible with respect to their the static PDE solve. So, and that's the reason why we can compute this Jacobian very efficiently. And this is a total computational time for the data generation. For instance, for the 2D and Navier-Stokes, we generate, let's say, the data without computing the Jacobian with this time, and also with the Jacobian, it's additional time, but it's not that much. It's about a quarter or 25% more of the computational time to compute the Jacobian. And we have some pre-processing to compute their linear spaces and also the training, because the training in the reduced space, right? So it's a very efficient for the training of the neural network. Okay, so this is a 3D example. It's the same as before, but we extended to 3D Navier-Stokes flow control problem. Here you can see we have the random inflow velocity, also control on the boundary, and our state dimension of their output would be 1 million, and for the input is on the 2D boundary, it's about 4,000. And we have the control, parametric control, is about 50 dimensional. The reduced dimension, we can still reduce to the dimension of 200, 100. By the way, the dimension here we reduced up to, depends on the decay of the eigenvalues or singular values if we compute it for the PCA, the KLE, or their POD. And so essentially, we need to maintain certain accuracy, like over 99.9% of accuracy for this dimension reduction. And then we compute here about 512 samples. We trained it with this number of samples. And so the test accuracy is about 1.5% in L2 error for the solution. And then so the evaluation of the neural network is about 10 million faster than the PDE solve, because each of the PDE solve takes about 30 minutes using 48 CPU cores. So here's a optimization result. Clearly can see there's a quite a large drag here, and it can reduce the drag here on the right. And the total computation for this optimization problem takes about less than 1 minute, compared to, let's say, if it just solve one PDE, it takes like 30 minutes in 48 cores. Okay, so let's come down to this summary. I believe the time is okay. So we have a PDE-constrained optimization problem, and we consider neural operator as a surrogate, and this surrogate can be used to address a lot of challenges in the high-dimensional input optimization problem, which require a lot of PDE solves. And our particular architecture, we use the Jacobian training, right? This Jacobian training helps with generalization accuracy for the solution operator, and also in particular for the optimization problem. And we use the reduced basis architecture and makes the derivative training scalable. Essentially, even though the discretization for the input output could be much larger, if we reduce it to the reduce the dimension, which is much smaller, we can compute this derivative information and also do the derivative informed training very efficiently. And then their online evaluation cost is very cheap. It's about 10 million faster reduction for the last problem, 3D problem, for instance. And then we can achieve about 10 to 100 more sample efficiency for the PDE solve for their optimization on uncertainty problem. And this cost includes all the data generation and training cost. And also, it could be very useful for amortization, because you might need to solve some other optimization problems, right? Like, for instance, if you want to use different objective functions, different penalty terms, and you can use the same neural operator to solve them. And also, if it becomes not so accurate, we can still use it as a control variant for multi-fidelity optimization on uncertainty, right? So this work is presented in this paper submitted recently. And also, last, I want to advertise a library that we developed. This is so-called SOPI, and it's a stochastic optimization under high-dimensional uncertainty in Python. So we released this library recently, and you can take a closer look. There is a SOPI documentation, how to install it, and I have a few different tutorials. Tutorial include this, OiO problem for the simple Poisson equation, and also we allow the MPI interface for the Poisson problem. For instance, we have like a very expensive PDE to solve. You can parallelize it over many different cores, or you have many samples. Now you can parallelize these samples over many different cores. Or if you have both many samples and expensive PDE to solve, you can also parallelize them properly. And we have additional, implementation of different risk measures like a super quantile conditional value at risk, and also chance constrained optimization. You can take a look at this library if you're interested. Thank you very much for your attention. Yeah, that's it. Some additional references.
Okay. Thank you very much, Peng. That was really great. So usually I start with questions, and then people can either ask through the chat, I think, or just send me a message, or just turn on their mic and ask. So just to start, I'm curious about sort of any kind of theoretical guarantees you can give here, because obviously in practice it seems to work very well, especially in terms of the computational time versus like the last example, right? So do you have any indication of theoretical guarantees that you will get an optimal solution of the original problem if you increase the network size or something like that?
Yeah, this is a very good question. So essentially, it depends on the let's say the accuracy or generalization property of the neural network, right? So you want to improve the accuracy, and you want to, in particular here, we use a derivative informed neural network to improve the accuracy. For the general theoretical guarantee, let's say we have this paper, a performance bound. There is some theoretical guarantee of at least the distance or the difference between your cost functional J, and we cannot guarantee the sort of like the error of the solution. That would require additional assumption like the convexity, but at least for their optimization in the PDE solve, I say there is a discretization error or there is a surrogate error, and on a suitable assumption of this surrogate, we can guarantee the performance bound for their cost functional.
But you don't know how to link that yet to the optimal value, for example, or the
that's right. This is some ongoing work. Essentially, we have to explore adaptive sampling. We have to balance these different errors. Essentially, there's a sampling error, surrogate error, there's an optimization error, and we have to properly balance all these different errors. That's quite a challenging computationally speaking.
I agree.
Yeah.
So before I ask another question, are there any questions from people in the audience? So then I guess my second question is, in the end, you replace a solution operator of a PDE by a different kind of random operator, essentially, right? You have this neural network.
Yeah.
Another kind of random operator. And then you solve a stochastic optimization problem where you use smooth C-bar. What is the solution you use to solve that smooth C-bar problem?
Say it again, please. What is the what?
Oh, like how do you solve the smooth C-bar problem? Is it what you said earlier, like LBF?
Yeah. So we followed the approach that I developed a few years ago. So we smooth it, and also we solve this minimization problem with respect to both T and also Z. And well, it depends on the smooth parameter, right? We used a quite aggressive smooth parameter, such that it's quite close to the original, let's say this guy here. And then we didn't account for the smoothing error in there, but this is essentially what we did.
So at least for the error, if you use that smoothing technique, if you have some kind of local convexity around the solution, then there's another paper that Drew and I wrote a couple of years after that one, where we do have a characterization of the error. It's basically, if you have local convexity around the solution, it's like the square root of the smoothing parameter. Otherwise, we have a better algorithm than just smoothing that we call the probability risk minimization algorithm. Adaptively updates the smoothing in a more natural way. So that might be, I mean, it's already quite fast, at least the thing you showed in the last page, like 53 seconds. I don't know if you're going to get that much faster with a different algorithm, but it's just a
Well, I guess the computational savings coming from the PDE solve, and if you use different optimization algorithm, it doesn't really matter which optimization algorithm you use, as long as your like derivative information is reliable, right? You can use different optimization method. Perhaps with a different optimization method, you would have a different number of iterations. And also maybe for the smoothing techniques, if you want to drive down the smoothing error, then you can adaptively change the smoothing of parameter. But if you use a parameter dual that can bypass this problem, it would be different optimization approach. It would be interesting to try out too.
Yeah, I could send you a link to the paper.
Yeah.
One thing I was thinking about, so the dimension of the decision space that you use for Z in the example is small because it's used like a parametrization of the function space. You get like 49.
Yeah, that's right. Yeah, exactly. So we assumed here we have a relatively small dimensional or moderate dimensional for the optimization variable to avoid it sort of like also another layer of dimension reduction here. So because, for instance, if the optimization variable in a function space, let's say it is simply in L2 space, right? We don't really know how to properly reduce this one just based on it is in L2 space, because L2 space is infinite dimensional, and you can properly parameterize it like using finite dimensional parameters here. But like for instance in the metamaterial design, it's a really infinite dimensional infinite dimensional optimization variable. And we cannot apply this current approach to there yet, because there's just too much variability in the optimization space, and our neural operator cannot properly loop through or see other possible solution. And one possible way is we can try to detect their intrinsic dimension of this optimization space by computing this sensitivity information. Because we have the Jacobian, and we can compute the active subspace type of dimension reduction, and then there we can use a projection, but it's not guaranteed.
Yeah, I wonder, because I have this recent work with Werner Römisch, where we look at stability and asymptotic statistics of a much simpler problem than the one that you looked at. And basically what I found doing like the computation of confidence intervals and the optimal value and so on, that the dimension of the control space makes a huge difference in the, let's say the variance or the variability of the optimal values that you see. So it could be that like as you increase your D sub capital Z here, that like the solution maybe is not as good as for the smaller dimension.
Yeah, exactly. For instance, like in one of our examples here, we used this from -4 to 4, right? So this is one constraint for our optimization variable. If we relax it to, let's say, like -40 to 40, then definitely the accuracy wouldn't be as good.
Oh yeah, okay.
Because you have like a lot more solutions to see.
Yeah.
Yeah.
That makes sense. I think that kind of also almost answers the question I had earlier about like the theoretical guarantees. Like I guess that could be a major challenge.
Yeah, exactly. That's right.
Also,
And there are some people like, for instance, they consider infinite dimensional field, but they assume certain correlation, like correlation of their optimization variable, let's say in a Merton kernel type of a correlation. And if you're aggressive enough, essentially, then intrinsic dimension, if you do the Cochran law of expansion, then intrinsic dimension is not that big, even though it is an infinite dimensional field.
right.
Well, this is due to their perhaps essential limit of this sort of like a surrogate model, because you cannot really see all the solution manifold if it is too large.
Right.
And maybe one thing that can help out is you can construct adaptively the surrogate model based on some local optimization manifold or local region, right?
Yeah.
Otherwise, it's just too challenging to solve.
So concerning the derivative informed problem,
you
mentioned that you can basically use the adjoint method within that training problem. So in the same sort of line of thinking, like you could probably also use second order information as well, right? If you think about sort of the usual efficient computation of Hessian vector products that you use in PDE-Constrained optimization, where you have a forward solve and like three essentially the backward solves. You could do that. Have you thought if that would make this even more accurate if you included somehow this curvature information, if you will, or this additional information? Or
we are actually working on it. There is this derivative training, and quite naturally, the second order training could be potentially helpful. Like for instance, this is a first order term, the zeroth order terms, first order terms, and second order term, right? Plus another second order term. And in the second order term, we need to first of all compute the Hessian action. And secondly, we need to compute the data for the training. And now, while the data can be efficiently computed by, let's say, the joint approaches, like the second order sensitivity information or incremental forward joint equations. And here, one thing we rely on is the automatic differentiation for the neural network. So there is a first order derivative here already, right? And so in the training, we need to take the derivative with respect to the neural network weights. So there will be like a second order derivative already. And then if you include the Hessian, there'll be like a third order derivative. So at the moment, like for instance, TensorFlow and PyTorch, they're not so efficient for very high order derivative computation. And JAX tends to be better in terms of their directional derivative. It's pretty efficient. And but essentially, if you go to high order derivatives for the neural network training, you have to commit the cost in there for the computation of the derivatives.
And in the training problem, what algorithm do you use for that?
For this training of this guy, we simply use Adam or AdaptW, for instance. It is a gradient best, right? Stochastic gradient best. And but here we have this Jacobian information, and then we'll compute the derivative of this Jacobian with respect to the neural network weights. Yeah,
because I saw something recently. So one of our postdocs here, Marius Steinhofer, was telling me about something called a natural gradient method that seems to be quite accurate. When using pins, at least.
Yeah, that's right. In fact, for this work we use Adam. but essentially the neural network itself is not that big, like it's in reduced dimension.
Yeah.
So in other work, we worked on optimal experimental design. We essentially we need to compute the map point, and there we used the map point maximum posterior point. We used their LBFGS. This is a quasi Newton algorithm.
Right.
Natural gradient flow is also another one. It's essentially trying to properly give you their preconditioner, like in the LBFGS.
Right.
So it would be helpful for this kind of smaller neural network, and also, if your data coming from like the PDE equations and it's very regular, or there's a lot of structure in here. But if you talk about like some machine learning in vision in language, that could be very challenging because the amount of data is very big, and also there is not so much regularity in there.
Right. Right. Yeah, I mean, the experiments I've seen of his were quite convincing. At least if you look at the error plots, like it behaves almost like compared to like Atom or Adagrad, those types.
Yeah. Okay.
Yeah, it's maybe worth looking at. But
Yeah, sounds good.
any other questions? Because I keep asking all the questions, but I don't know. I think people slowly have to.
Yeah, maybe. Yeah.
Let me stop recording for a second because it's